Hello there, Mr. Sutton here with the Pre-Cal Honors 9-3 Extra Practice Number 1 solutions on algebraic limits of polynomial and rational functions. On this problem, we're trying to find the limit of this polynomial as x approaches -2. Now, since this is a polynomial, we know that the limit and the function value are going to be the same thing, so we just have to plug in -2 to see what this comes out to. So that's going to be 2 times -2 minus 3, so -4 minus 3, which is going to be -7. This problem is an example of something that's so easy it might be difficult if you overthink it. We're just trying to find the limit of a horizontal line through y equals 2 as x approaches 1. Well, this graph is going to be approaching the same y value everywhere, including 1, and that's just going to be the y value 2. On this one, we're trying to find limit as x approaches 3 of this cubic function. Now, since this is a polynomial, we know the limit and the function value are going to be the same thing because this is continuous. So we're just going to plug 3 in and see what happens. So I've got 3 cubed minus 3 times 3 squared. So 27 minus, well, another 27 comes out to 0. To find the limit on this rational function, we always have to be asking ourselves, is this worth factoring? And while we could factor out the denominator, it doesn't look like there's anything that's going to cancel with this numerator. So I'm just going to go straight to plugging 2 in here. So we've got 2 plus 5 over 2 squared minus 3 times 2. That's going to be 7 over, let's see here, we've got 4 minus 6, so -2. So that comes out to -7 halves. And since that actually exists, we know that this is going to be the limit. It's going to be the same as the function value. To find the limit as x approaches -2 on this rational function, we could try plugging -2 in at the very beginning, but right away if you do that, you'll notice that we have -2 plus 2, which comes out to 0, and there's a pretty good chance that the numerator also comes out to 0. This looks like it's factorable, so I'm going to go ahead and factor it, and even if I can't cancel anything, that'll probably make it easier to plug things in. So the numerator, I need 2 things that multiply to 8 and add up to 6, so we can write this as x plus 2 times x plus 4. And I see that actually we can cancel out these x plus 2's. So that leaves me with limit as x approaches -2 of x plus 4. Now it's important that this limit stays around here because we're not saying that these 2 things are equivalent because we're not even mentioning what happens if x is -2. We're saying the limit is equivalent. So now that I've got the problem factor here canceled out, I'm just going to plug -2 in to see what this was approaching. That's going to be -2 plus 4, which comes out to +2. On this problem, I'm trying to find limit as x approaches -2 of this rational function. Can't really do much to simplify or factor this, so I'm just going to go straight to plugging in -2. So let's see, we've got -3 over -2 quantity squared minus 4. So down in the denominator, this is really 4 minus 4, which is 0. So this all comes out to -3 over 0, which is going to be undefined. That means since we're getting something that's not 0 over 0, that means that this is just a straight up does not exist. Can't really do anything else with this. For this one, I want the limit as x approaches -4 of this rational function. Now, if we go straight to plugging in -4, you'll notice that we get a 0 in the numerator. Don't know about the denominator yet, but it looks like I can factor the denominator, so I might as well do that. In the worst case, it'll just make it a little easier to plug in -4. So 2 things that multiply to 20 and add up to 9. That would be, we'll have x plus 4 and x plus 5. We've got the limit around still, and don't forget we still have this negative out in front, so a few details you want to be careful about. Now it looks like I can cancel out these x plus 4's, which is good because if I just plugged -4 in at this point, we would end up with 0 over 0, which is no good. So plugging in or canceling out right away here, we end up with -1 over x plus 5. And now if I plug in -4, I've got -1 over, well, this is just going to be 1 down here, so that's a grand total of just -1. For this problem, I have a rational function that I'm taking the limit at -6 for. But if I plug -6 in, right away I notice I'm going to get 0 in the denominator. And I mean, that might be the way this one shakes out. But before I go ahead and plug in -6, let me see if I can factor the numerator. In the worst case, it'll just make it all a little bit easier to plug things into. So things that multiply to 24 and add up to 10, that would be x plus 6 and x plus 4. And now I see that I actually can cancel out these x plus 6's, which is good because if I plug negative 6 in, that's going to give me 0 over 0, so I definitely want to get rid of that if I can. So now I've got limit as x approaches negative 6 of x plus 4. Well, at this point I can just go ahead and plug in negative 6 since I canceled out this problem factor here. So negative 6 plus 4 ends up giving me a final limit of negative 2. For this problem, I'm tempted to just kind of plug a 3 in the beginning, but I know if I do that, trying to find this limit, that I'm going to end up with 0 in the denominator. So let me see if I can factor the numerator and cancel that out. Maybe I can, maybe I can't, but we don't know until we try. Things that multiply to negative 6 and add up to negative 1, we're going to have x plus 2 and x minus 3. And it turns out that we can cancel out the x minus 3's, and we want to, so we don't end up with 0 over 0 when we plug 3 in. But now that I've canceled that out and I've just got x plus 2, at this point, to take the limit, I can just plug 3 in for x. So that gives me 3 plus 2, which comes out to 5. To find the limit as x approaches 4 of this rational function, before we plug in 4, let's see if we can factor the denominator. And the reason I'm doing that is I notice that I'm going to get 0 in the numerator. So there's a pretty good chance I get 0 in the denominator as well. I'm probably going to have to cancel things down the road, so let me just factor right away to begin with. So two things that multiply to 28 and add up to negative 11. We'll have x minus 4 and x minus 7. X minus 4's do end up canceling, so that means there was going to be a 0 over 0 if I tried plugging 4 in immediately. So now that those are gone, I've just got 1 over x minus 7. Plugging 4 in at this point, we have just negative 1/3. For this problem, to find the limit as x approaches negative 5, at some point I'm going to have to plug in negative 5, but if I do that right away, I end up with 0 in the numerator, which is going to be a problem if I also have 0 in the denominator. Let me factor this and see if there's anything that is going to cancel. Things that multiply to 35 and add up to 12, that'd be x plus 5 and x plus 7. So these x plus 5's do end up canceling, leaving me with 1 over x plus 7. And now if I plug in negative 5 for x, I'm not going to end up with 0 over 0 like I would have up there. So this is going to be 1 over negative 5 plus 7. And then that's going to end up being just 1/2. For this problem, I'm trying to find the limit as x approaches 5 of this rational function. So it looks like the denominator actually could be factored, but there's nothing to plug an x for in the numerator. There's no way I'm going to end up with 0 over 0 for this. So really, I might as well just go straight to plugging in, and if I get something that's not 0 down here, great. If I get something that is 0, either way, I'm going to get a final answer. So plugging 5 in for x, we're going to end up with, let's see here, we got 25 minus 50 plus 25. So that's essentially 50 minus 50, which is 0. So we end up with negative 3 over 0. That's undefined. So because it's not 0 over 0, because it's something that's not 0 over 0, that means that this limit just flat out does not exist, and the problem is over.